Hi guys, so this will now be a video that we use to go through the changes or states that the JK flip-flop will go through before it stores values in Q and Q complement. So we'll be observing the truth table of this gate soon. Now, before I go into the details of the JK flip-flop, I want to give you guys a small disclaimer. As far as your syllabus is concerned, knowing how values pass through the JK flip-flop and how changes are made are not necessary, right? But knowing that helps you a lot, and that will help you get a better understanding of the JK flip-flop. But that level of description I will not be doing in this video, just to keep this video simple. If you are interested in learning about how the JK flip-flop actually works internally, how values pass through and how values propagate through, I would recommend a video channel called Computer Science. I'll share the link of this channel in the description. It's an amazing channel that has wonderfully animated videos of how SR latches work and also JK flip-flops work. And it also accompanies these diagrams with clock signals, so you can understand how the clock changes and the respective clock changes result in the JK flip-flop changing as well. So I would, of course, link that in the description so you can watch that in your own time. But for the moment, we'll just be understanding what the JK flip-flop has as its states, meaning what will happen to Q and Q complement when J and K changes. We are now going to look at the internal workings of the flip-flop itself. Now, before we look at the truth table, I want you guys to understand a small thing. In the JK flip-flop, this portion of the JK flip-flop is basically where our data is stored. This is the part that is responsible for the storage. This is sort of like a latch, meaning it latches on to a bit of data. But this part isn't storing data, right? This part's responsibility is to validate the inputs coming in. So this is sort of like a validation layer, right? Meaning whatever that is passed on to the latch is only passed on if the J input, the CLK input and the K input are true for the respective gates. So the idea is we are having this sort of layer of security in front, which only allows values to propagate through into the next layer if and only if the current layer's values are true, meaning in this NAND gate it makes sure that only values go through if Q complement is true, J is true and the clock is true. For the NAND gate below, it only allows values to go through this NAND gate if the clock is true, the K input is true and Q is true. So the idea is it's sort of acting as a validation layer, or a layer that's a master to the layer in front that prevents values from going through, and also prevents this sort of race condition which we discussed in last class, which means that it doesn't allow for just user inputs to inflict changes upon the state stored in the latch. It will get user inputs, meaning J and K, but it will stabilize them by passing it through an AND gate via a clock signal, which means that no matter what changes we make to J and K, they will only go through the circuit if the clock signal is actually high. So in summary, you have two sort of layers to this circuit. The first being the validation sort of layer, which makes and ensures that the signals coming in are correct and make sure that it's stable before the signals actually pass through into the next layer, which is actually responsible for storing the data. So really, this part of the circuit is sort of combinational, meaning there are no persistence parts here. There is no memory of sorts, but this is the actual sequential layer, right? This is the part that is responsible for storing the data in its full glory. Right, so let me clean this up, but hopefully that made sense to you, right? We just have a bunch of sections to this logic gate circuit, the JK flip-flop, part responsible for validation, and part responsible for actually latching on to data. All right, so just like all the other logic circuits, we will be starting the logic circuit assuming a bunch of starting values or a starting configuration. The starting configuration will be as follows. We assume that S is 0, R is 0, Q is 0 and Q complement is 1. Now you might be wondering, okay, there is no S and R here. Why have I written S and R here? Actually, S and R are to be replaced by J and K, but realize and understand that J and K are effectively the same in meaning to S and R, right? J is a set input, K is a reset input. We've just changed the names because it's now referring to the inventor Jack Kibley. Right, so let's fill the table up with this initial configuration. So notice how this table doesn't just have Q and Q complement as its only two outputs column. It has two subsections of output columns, one for clock low and one for clock high. Okay, how does that work? The idea is this clock or this output column basically shows the outputs when the clock is low, meaning when the clock signal is in these states. But this output column shows the outputs when the clock is high, when the clock is in these states, right? So we can realize what happens before the clock is ticked and what happens after the clock is ticked, so that it's clear to us how the Jack Kibley flip-flop is operating. So at the beginning, regardless of whether the clock is low or clock is high, when J is 0 and K is 0, Q and Q complement will be 0 and 1. The same will be after the clock ticks as well, 0 and 1. So this is before the tick, this is after the tick. Technically what should happen is JK flip-flop should only persist changes or make the gate actually store or change when the clock ticks, not when the clock is not ticking. So any changes we make will happen only when the clock goes from low to high. Right. What am I going to do to the J gate next? After this, we'll be making the J input 1. So the idea is, remember, the J input is similar to the set input. So what that should technically do is it should change the Q from 0 to 1. Meaning when you change J to 1, it should make Q store 1. It should set the Q to 1. So what I want you guys to understand is, before the clock signal, it will basically be whatever was previously put in it. 0, 1. So we're taking the values from the previous stage here. Right? The values from the previous stage come here. Let me actually draw those lines a little bit more beautifully. Like that. Okay. The values from the previous stage coming. But then after the clock ticks, when the clock becomes high, only then would the changes persist. So what is the change we're going to inflict? We're going to change the Q to become a 1 and Q complement is going to go to 0. So now it's going to become 1 and 0. Right? So previously it's the same as the previous stage before the clock signal, and once the clock signal turns high, the clock ticks, or this 0 goes to 1. That's what it means by a clock tick. Then only the changes will actually be made. So 0, 1 will become 1, 0. Right? Okay. And then what I'm going to do is I'm going to set the J input back to 0. So we are getting it back to the original state. Let's see what happens. So what happens is, of course, the current state of the gate before the clock signal ticks is going to be whatever was previously put in it. So which is the 1 and 0 that was previously put in it. Let me draw two arrows to say that those two inputs, or actually those two outputs, are from the previous time interval. And then what happens when J and K are both 0? Nothing happens. It's just going to persist. It's just going to store whatever was previously put in it. So it will basically latch on to the 1 and 0 that was previously put in it. What am I going to do next? Let's make the K input 1. The K is effectively the same as the reset input. So what should happen is it should result the Q from going to a 0, right? Whatever the Q was earlier, it should make it go to a 0. So whatever the Q was earlier is a 1, right? Q was 1 earlier. So Q was 1 and Q complement was 0. What will happen after the clock signal turns high? Since the K input is high, it will result in Q becoming 0 and Q complement becoming 1. Right? So realize that the changes to the Q output only persist or only change when the clock signal ticks from low to high. Right, and then finally, here's an interesting one. What happens when both J and K are 1? Now in this scenario, of course, we need to take in whatever was previously put in it, 0 and 1. But what happens is, earlier, we would have resulted in this fault condition where both Q and Q complement is the same. But when J and K are both 1, we don't result in a fault condition. The outputs just toggle, meaning whatever Q was, it becomes its opposite now after the clock ticks. It becomes 1. and whatever q complement was, it becomes its opposite, 0. So although this seems like the reset this seems like the set configuration because we are only looking at it in one time interval. In the next time interval, if you have 1 and 1 still going into the circuit signal, the 1 and 0 from the previous state will become a 0 and a 1. So it's going to toggle 0 1 1 0 0 1 1 0. It's going to keep on toggling. That's what happens when the JK flip-flop has two inputs of both ones. So you're now no longer in a sort of a fault condition. Q and Q complement are always its opposites, but it's going to keep on toggling in that case. Right, so that's the debugging of how the JK flip-flop works. You can of course go through the video series I recommended in the description to understand how these changes actually go through the logic circuit and those changes are made. But this is just a simple realization of those changes just by the truth table itself. So this state where J and K are both 0 is what we consider the memory state, where it's actually latching on or storing the data. When J is 1, we are in the set state. When J and K are both 0, it's still in the memory state. Whatever was in the initial row, the same operation happens now, still storing data. When J is 0 and K is 1, it's in the reset state. And when both J and K are 1, it's no longer in a fault condition, it's in something called the toggle state, which means that it's going to alternate between 0 1 1 0 0 1 1 0. We'll see this in action in the practical video that I'm going to have soon after this video on my playlist. Right, so let's now simplify this. What you see here is the simplified version of the same JK flip-flop. Notice how you have a bunch of values for J and K, but the clock signal is always 1. The reason I've only displayed the clock signal being 1 and not being 0 is because when the clock signal is 0, nothing happens. It's just going to store whatever was previously put in it. So there's no real change that we'll notice when the clock signal is 0. So there's no point looking at it in this simplified truth table. The changes are only made when the clock signal is 1. So I've just filled the clock signal column with 1s. The rest have of course undergone changes. And similar to how we describe the SR latch, the changes are made such that the first stage is memory, the second stage is set, the third stage is reset, and the final stage is toggle. But in the case of an SR latch, it was fault. Now, I want to connote to one more thing. Remember I told you when you go from one state to the next in the debugging truth table, the one that we do step by step, when we go from one state to the next, I only make 1 bit changes. I only make 1 bit changes, not multiple bit changes. That is still very important with the JK flip-flop. You are not supposed to make 2-bit changes unless it's necessary. So you're only going through changing one of the bits at a time when you're going from one state to the next. Of course, in the simplified truth table, just to avoid this duplicate memory state, I've reduced it to just 4 rows. So from this stage to the next, you might see that there are 2-bit changes, but that's okay because this is the simplified truth table, just shows what's changing. So the final truth table has a memory state when J and K are 0, a set state when J and K is 1 and 0, a reset state when J is 0 and 1 is J is 0 and K is 0, and a toggle state when both J and K are 1. It's pretty simple, right? And remember, in all those states, K is always 1. Alright. What you see on the left, or actually the right here, is the algebraic format of this same truth table. The idea is, when J and K is 0, we are in the memory state, which means that Q at the current time interval is whatever was Q in the previous time interval. So Qt is equal to Qt minus 1. Q complement T, that is Q complement in the current time interval, is equal to Q complement T minus 1, that is the Q complement from the previous time interval. When J is 1 and K is 0, we are in the set state. When J is 0, K is 1, it's in the reset state. So whatever these two states, Qt is J and Qt complement is K. So whatever values go into J, those propagate into Qt. Whatever values go into K, those propagate into Qt complement. So that's what happens when you're in J equals 1, K equals 0, or J equals 0, K equals 1. You can confirm these values by looking at the truth table. And what happens when both J and K are 1? When J and K are 1, Q and Qt undergo alternative changes. It toggles. So Qt basically becomes q complement t minus 1. Whatever q complement was in the previous state, it's going to become the q now. And whatever q complement is now is going to become q from the previous state. So if qt was, actually we'll not look at qt, we'll look at qt minus 1. Let's imagine q complement t minus 1 was 0 and qt minus 1 was 1. What will happen now is that 0 will go into the qt now, and that 1 will go into the q complement t1, q complement t now. And what will happen is, when you look at the equation again, this q complement t will be the q complement t in the next time interval. So it will be 1 next, that 1 will propagate through into qt, and this 0 will be, or this 0 will be the qt minus 1, and that 0 will be passed on to the next qt. So this might seem like a bit too confusing for you. Of course, the truth table is all you need to know, but this is just the algebraic form of the same thing. Basically, it's undergoing toggling. Whatever the previous state was, it's going to be the opposite for q and qt complement. Right. That's all there is for the JK flip-flop. In the next video, we will look at how this JK flip-flop works in a practical scenario.